One comment before we get started. I thought about what to put in the final exam. And I think I'll give you a heads up. You should learn how to work these problems. Don't just memorize answers, because I'm going to change the parameters and the answers will be different. Okay. But if you can do everything that we've covered in here, then you should be fine on the exam. Okay. All right. Number 45. All right. Nitrogen has 5 valence electrons. Is that true? Yeah. Count from the left. 1, 2, 3, 4, 5. Nitrogen has 5 valence electrons. That's if it's neutral. Which of the following configurations represents the ground state for N minus? So if we add a minus, we add an electron, right? So we got 6 electrons. All right, so start from, and the choices here are only valence, right? We left out the 1s. So we're starting, we would write 1s 2, but then the valences would be the 2 s's and the 2 p's. And that's where these 6 electrons go. So we'll have 2 here and 4 there. Right? Okay, so we've got 1 here that can do that. And we've got 3 here that can do that. Hund's rule. Got to have 1 in each degenerate orbit before you can start pairing them up. So we should have a pair, and then 2 lones. Let's see. Pair E. E should be the correct answer for this one. Okay. .46. Okay. So if you're given this electronic configuration, where we have the core is argon, I'm going to put the atomic number in there. 4s2, 3d10, yep, and 4p2. Question is, which one of which would this be? Non-metal, transition, metal, lanthanide, or metalloid? Look at your periodic table where you find argon, and then swing to the next level, right? 4s1 and 2 is potassium, calcium, then we go across all 10 of them through the transitions. Now we're back into gallium, germanium. That's germanium. Now, what is it? With germanium, notice where the line, the zigzagging stair-step line is. Germanium is right next to it. Right? That means it's probably a metalloid. Sometimes it acts like a metal, sometimes it acts like a non-metal, depends on the environment. So if you have metalloid as a choice, take that one. If metalloid's not there, then you call it a metal. Okay? All right. Hmm. 47. Which of the following groups do all the elements have the same number of valence electrons? They'd have to be in the same group, wouldn't it? All right. So we look, silver, cadmium, argon. Well, argon, that lets the first 2 out. Right. How about sodium and calcium? They're in 2 different groups. Alkaline metal, alkaline earth. So it can't be that one. Phosphorus, sulfur. Nope, they're in 2 different groups. So is chlorine. They're in 3 different groups, actually. Phosphorus, arsenic, and selenium. Phosphorus, arsenic. Oh. Phosphorus and arsenic are in the pnictogens, but selenium is a chalcogen. So none of them are right. Right. All right, 48.
I have a question then.
Yes, ma'am.
The argon, you said that automatically made it out. How come? Because it's a noble gas?
Yeah.
All
It's,
noble gases are,
no, it's just the wrong group. Yeah. Yeah, I wasn't making,
if they were all noble gases, then it would be,
that's one. They all have the valence. They have 8 valence electrons if they're all noble gases, yeah.
oh,
Mhm.
just wanted to make sure I was.
Yeah, the condition is that it be in the same group. Right? If they're all in that group, or all in this group, or all. And you can be sure that you're not going to have any transition metals in there, unless it's one that doesn't match. You won't have 3 transition metals because they're just screwy, right? They don't play well with others. Only the representative elements, the first 2 and the last 6, where you can actually say something about the valence electrons. Okay, 48. Which of the following was not an elemental property usually predicted by Mendeleev for unknown elements? Well, okay. The first one, electronic configuration. In his day and time, there was no such thing. They had no idea about electrons configurations. All they knew was behaviors, similar behaviors, and they were just barely getting a handle on moles and numbers of things. The rest of them he did know about. Atomic mass, density, boiling point, oxide formula, those, he knew all of those and used that information to predict their characteristics. All right, 49. Let's see, which of the following statements is always true concerning a reaction represented by the following balanced chemical equation? Okay, let's write this one up. C2H6, is it? See it better this way. And 7 oxygens. This is a combustion reaction. And we're going to make that one a liquid. CO2. Okay, what are our choices? Gives us an idea of what we're headed for. If we have equal masses of the 2 reactants, there's no limiting reactant. Number of moles. So we're talking about limiting and excess. That's where we're headed with this. All right. So if the stoichiometric ratio is 2 moles of ethane to 7 moles of oxygen. So what would that look like in terms of mass? Okay, we need the molar mass of ethane, right? 2 times 12.01 and then 6 times 1.01. We get the calculator out. Because a lot of those questions have to do with mass. Let's see. You got it already? Yep. Okay. So 2 moles converted to mass. That's 3008 one. So 2 times that would be 60.16 grams. 60.16 grams. These are stoichiometric amounts. Oxygen would be 32. So 7 times 32 is 224. 224 grams. That would be a stoichiometric ratio. So if we have, if the ratio is such that this is insufficient, of course, then that's our limiting, and vice versa. So let's see what our choices are. If we have equal masses, there's no limiting reactant. Equal masses means that just pick one of them. Right? If we pick this one and say that one is 60, then that one's limiting. If we pick this one and make that one 200, that was still limiting. Right? So equal masses means oxygen's limited. Let's see. Yeah, A. Let's just put those up here. A. Equal masses means oxygen is limited. How about B? So A is not the right answer. If we have an equal number of moles, there is no limiting reactant. Equal number of moles. Now, if you have 2 here and 2 here, then the oxygen's limiting again. Right? So equal moles also means oxygen limiting. All right, so that can't be it. How about C? If we have more mass of C2H6 than O2, then O2 must be limiting. What that should say is if we have more mass of this one than that one, right, then oxygen must be limiting. If we have equal masses, then oxygen's limiting. So if we have equal masses, say we have 60 and 60, but if we have more of this, oxygen's still limiting. Right? So that was true. If we have more mass of ethane, then still oxygen is limiting. But it can't be E because we've already found one that's true. If we have more mass of oxygen, then C2H6 must be limiting, and that's false. All right. So this is the only one that can satisfy the conditions that were given in the problem. And the way we figured that out was we saw what they were looking for. They were looking at masses. So we said, okay, we're going to convert these number of moles to masses because this mole ratio is stoichiometric, this mass ratio is stoichiometric. Anything different than that, one of them is limiting. All right, 50. Which of the following is paired incorrectly? Got A, B, C, D, and E. All right. What about sulfuric acid? Is that a strong acid? Yeah. Strong acid. That's correct. How about HNO3? Weak acid? No. That's wrong. That's paired incorrectly. So we found our answer. But if we look at the others, we find that this one, barium hydroxide, is, remember, all alkaline metal hydroxides and alkaline earth hydroxides are strong. Barium is an alkaline earth. So this would be a strong base. That one's correct. How about this strong acid? Yeah, we know that one. Hydrochloric acid is a strong acid. And NH3 ammonia is a weak base. Okay. Now, what does that mean in terms of Bronsted-Lowry? It means that if you put that in water, right, it reacts with water. Where's the equilibrium? It's over here. You would produce some of this and some of that. And that gives it its basic character. But most of it is over here. It's a weak base. It doesn't go after too many or very strongly protons from a water molecule. Okay, that makes it a weak base. So if this is a weak base, what does that make this? Strong acid. Okay. It's 50, yep. 51 through 53 is based upon aqueous solution of barium chloride and silver nitrate mixed to form solid silver chloride and aqueous barium nitrate. We didn't even make you guess that silver chloride was insoluble. We just told you it was. Molecular equation, ionic equation, net. Okay, so we're going to run through the whole gamut here with barium chloride. Let's see, 51, 2, and 3. Barium chloride in aqueous solution. Is that right? No, barium's an alkali metal. Alkaline earth, right? Yeah, so it has a 2+ charge. That means we need 2 of those. Right? And then silver nitrate, correct? Yeah, silver nitrate. Silver is a 1+ charge, nitrate is polyatomic with 1+, and it's completely soluble. And then what it forms is, and let's do, to keep it in the correct order. I want silver chloride first. Okay, so we'll take, this is an exchange reaction. These two guys swap places. So silver associates with chlorine. And it's insoluble. And then the barium associates with a nitrate. That's a +2. This is a -1. That means we need 2 of them. But it's completely soluble. Okay. That's the first trick. Get those things written correctly.
You said it's an exchange.
Yeah, it's a double displacement or an exchange reaction. These guys just swap places. Okay, so let's balance. These types of reactions are usually really easy to balance. You don't even have to use the budget method. Right, we've got 1 barium here, barium there. 2 chlorines here, we need 2 chlorines here. Okay, that gives us 2 silvers. 2 silvers here, 2 nitrates, 2 nitrates there. That's balanced. That's the balanced molecular equation contains which of the following terms? Well, 2 silver chloride, yep, does that. 1 silver chloride, no. And we also need the phase. So 2 AgClS is true. Let's see. Now we want the complete ionic equation. That means if it's an aqueous solution, it actually exists as independent ions. Barium 2+ in aqueous. And then 2 chlorides. And 2 silvers. On the reactant side, they're all in aqueous solution. And then on the product side, we still have this one solid. We can't split that one up. But we do have barium 2+ in aqueous and 2 nitrates. That's the complete ionic equation. And we can't reduce it any further because there's only 1 barium each. We can't divide by a whole number and make it simpler. So that's it. So to answer the question, we're looking for which of the following terms is in this one. Let's see. There's no 2 barium 2+ is not there. 1 chloride is not there. We need 2 of them. 2 silvers in solution. Yeah, that was there. Single nitrate, no. Silver chloride, aqueous, no. So this is the only one that's selectable out of those choices. And then the net ionic equation. How do we get there? We take the spectators and just cross them out. Right. So the best way to find the spectators is to look at the solid. Silver has to stay here. Chloride has to stay here. But barium's the same on both sides. Nitrate's the same on both sides. Cross those out. Cross those out. And that's the net, except, look, 2 chlorides, 2 silvers, 2 silver chloride. We're going to reduce it, right, to its simplest whole number ratio. Chloride plus silver yields silver chloride. That's the trick to this one. So when you look for the answer, you're not going to see any 2 coefficients. Like silver aqueous, yeah, that's in there. Barium's not there, nitrate's not there. Hydrogen ions have never been there. And silver chloride aqueous is just dumb because silver chloride is insoluble. Can't be aqueous. So the only possible one is the silver aqueous. Okay. So 54. See, you got 2 balloons, orange balloon and blue balloon. This one looks familiar. I can't read it. I got something in the way there. Let's see, blue balloon filled with neon is in the orange balloon. Orange. And argon is in the blue, correct? Orange balloon is filled neon, blue balloon. Okay. The orange balloon has twice the volume. Okay. So the volume of the neon balloon is equal to twice the volume of the argon balloon. Okay. Which of the following best represents the mass ratio? All right. We have to assume that these balloons are in close proximity and the temperature of this one is equal to the temperature of that one. The volume's different. And the pressures are the same. Otherwise, we can't answer the question. So if that's true, and this one is twice the volume of that one, what does that say about the moles? That means the moles of neon, twice the number of moles of argon. Okay. So how much does each argon atom weigh? It's about 40, right? It's about 40, argon, 40. And neon is about 20 in the neighborhood. Oops. Okay. So if there are twice as many neon atoms as there are argon atoms, if they were the same mass, then this would be twice as heavy as that one. But this one's half the mass of each particle. And even though you have twice as many particles, each one is half the mass. So their masses are equal. Right? So the mass of neon is equal to the mass of argon. All right. So the ratio is 1 to 1. All right. 55 coming up. Uh, 45.9 gram sample of metal is heated 95.2 degrees and then placed in a calorimeter with 120 grams of water at 21.6. The final temperature of the water is 24.5. Which metal is used? Okay, we're going to identify the metal based upon its specific heat. So that means we need to know some facts first. We need to know first the metal and the water. So we need to know the mass of the water. We need to know the mass of the metal. Okay, let's get those two first. Mass of the water is 120 grams. And the mass of the metal is, where is it? I know, oh, 45.9. 45.9 grams. Okay. The specific heat of the metal is unknown. Specific heat of water is known. 4.18, is it? That's joules per gram degree C. Okay, what else? We need to know temperatures. What's the initial temperature of water? The initial temperature, let's see, let's designate these. There we go. And then the final temperature is going to be the same for everybody. So the final temperature is 24.5 degrees C. The initial temperature of water is lower than that, 21.6. And then the initial temperature of the metal is 95.2. There we go. Now, our calorimeter is an isolated system. That means that whatever happens in Vegas stays in Vegas. Everything that happens in there is, in terms of heat, is equal to 0. So we can calculate the heat for the metal plus the heat for water, and we're not given the calorimeter parameters. We have to assume the calorimeter has no effect. All right, then we expand these. What is Q equal to? Q is equal to the specific heat of the metal times the mass of the metal times the change in temperature for the metal. And the same thing for the water, only with its different terms. Like specific heat for water, the mass of the water, and the change in temperature of the water. Okay. See, it's getting complicated really fast. That's why I wanted to put all this stuff up here in its proper place. Then we can be sure we can get it into the formula in its proper place. All right, specific heat of the metal is our unknown. The mass of the metal is 45.9 grams. Okay. And the temperature change is final minus initial. So the final temperature is 24.5 minus the initial, 95.2 degrees C. Okay. Let's see, let's keep these separated. For water, we've got 4.18. Yeah, joules per gram degree C. Then we got the mass of the water, 120. And then change in temperature for the water. Final minus initial, 24.5 minus initial, 21.6%. All right. The thinking part's done. The rest is crunching numbers. So if we take this term, resolve that term times this one, and that'll be times that. So I got 24.5. Oops, I'll do that again. Minus 95.2 is 70.7 times 45.9. That's minus 3245. Okay. And then plus whatever's inside this one. 24.5 minus 21.6 is 2.9 times 120 is 348 times 4.18. And that's 1,455. And this grams canceled. Degree C canceled, so this is actually joules. And this is, what is this? Degree C. This is gram degree C here. Gram degree C for that part, times whatever this is. Okay, so we gotta resolve our equation for that one. If we put that one over here, it's a minus 140, 1455 equals minus 3245. Right? Times there. So SM, we just say this divided into that. And the negatives cancel. 3245. And that should tell us what our specific heat is for the metal. I get 0.448 joules per gram degree C. Who's that belong to? Looks like iron. 0.45 is iron. Correct? Unless I made a math error. Well, at least it agrees with the key. Okay.
This one will change then.
Yeah. Right, unless the class agrees to do it Thursday. Need another couple of days. Tuesday's okay, or you want Thursday?
I'm cold too.
Tuesday? Okay. I'll be here Tuesday then. Let's see. All right. 56. Got other exams on that day?
I don't have a math exam, but it's not fun.
Okay. For which of the following transitions does the light emitted have the longest wavelength? Longest wavelength implies lowest energy and consequently the lowest frequency. Oops, wrong symbol. So I look at lowest energy. Lowest energy means the shortest transition for the electron. Right? If it's going from level 4 to 1, right? A, B, C, D, and E. If it's going from 4 to 1, that is a huge jump compared to 3 to 2. Right? If you look at your atom, you got N equals 1 here. And then you got maybe 2 is out here. And then 3 is a little closer. 4 is even closer to that. All right, so 4 to 1 is a huge jump. 3 to 2 is lower energy. Have we got a 4 to 3? Oh, yeah, we do. D. 4 to 2 would be big. 4 to 3 would, out of that group, 4 to 3 would be the shortest jump and the lowest energy, which means the longest wavelength. Okay, so that would be D. 4 to 3 would emit the longest wavelength. Is that still a mystery? And think like an electron. Which of the following?
I guess it would take the lowest energy to get from 4 to 3, right?
Well, if you went from 3 up to 4, it would absorb the least amount of energy. Or if you went from 4 to 3, it would give up the least amount. Because as you get closer, right, electrons that are closer to the nucleus are lower in energy. So if you go from a higher number to a lower number, it's going to give up light. Or if you advance, if you promote an electron from a lower level to a higher level, it absorbs light. And it's exactly equal. This is quantized
And
energy.
the further you get away from the middle, the closer they get, right?
Yes,
Which makes it the shortest.
right. If you're way, way out here, like you went from 8 to 7, that would be even shorter. Yeah. Which one of these is incorrect for designating an atomic orbital? Let's see, what do we have to choose from? 1s, 6s, 3d. 1s, 6s, 3d, 1p, and 4f. P, 4f. Okay, remember our quantum numbers. N, L, M sub L, and M sub S. We don't have to worry about these two because we're looking at N and L here. So remember, N can be anything from 1 on up to whatever. L can be, depending on which one of these it's at, it would be from minus N up to 0 up to plus N. Right? No, I'm sorry. That's M sub L. Sorry. Scratch that. Jury, please disregard that witness. That's for this one. For this one, it's 0, 1, 2, up to N minus 1. There you go. Okay. So, and we give these numbers, these L numbers, letters. 0 is S, 1 is P, 2 is D, 3 is F. So that's where we're at here. So if you're at level 1, can you have an S? Yeah, 0. That one's good. If you're at 6, can you have an S? Yeah, you can have 6 can have 0, 1, 2, 3, 4, and 5. Right. So S is good for 6 also. How about 3D? Let's see, 3 can be 0, 1, or 2. S, P, or D. Yep, that's good. 1, can 1 have P? Nope. 1 can only be 0. So that was bad. And 4, can 4 have F? Let's see, 4 can have 1, 2, 3, 4, 0, 1, 2, 3. Yep, that's good. That's how you figure that one. Just as a side note, I learned this past week, I've been watching a series. Did I tell you about that series called The Atom? Yeah.
Yeah.
Turns out Einstein hated quantum mechanics because it's based on probability. And Einstein was certainty. He was old school. He had to eventually give in though. Okay, 58. All right. In the molecule, xenon difluoride. What? How many electrons surround xenon and what's the molecular geometry? How many electrons surround xenon? It doesn't say whether they're bonding or non-bonding, just how many are around xenon. Okay. So xenon's going to have 8 valence. This is going to have 7 times 2. So that's 14 plus 8 is 22, right? Electrons. So we put xenon here. Oops. Fluorine. That's 2, 4. And we're, oops, I think I miscalculated. No, that's right, 22. This is 18. Yeah, 18. Okay, 2, 4, 6, 8, 10, 12. Used up 12 now to make our octet around fluorines. So we have 6 left over. They have to go on xenon. There's no other place for them to go. So 2 there, 2 there, 2 there. So that's 1, 2, 3, 4, 5. We have 5 pairs of electrons. 5 pairs or 10 electrons. And the geometry is, let's see, how many electrons surround xenon? How many electrons? You know, that's not worded correctly. It should be how many unbonded electrons surround xenon. Yeah, because there's no answer in there with 10. So it needs to be how many unbonded electrons there are. There are 6 electrons. And it would be, electronics geometry would be trigonal bipyramid, right? You have xenon in the middle. You have fluorine here, and your lone pairs there, there, and there. That means the molecule is linear. Okay, so well, what's the only bond angle in here? 180 degrees. That's your only choice. You do have to know that in trigonal bipyramids, when you have lone pairs, they go on the triangle. Unlike octahedrals. Okay. There's a difference. And that leads to, right, because if you did 2 here and 1 there and put your fluorine over here, that would be bent right angle. Right. So you do have to know that all these lone pairs go on the triangle. That makes linear. Right. Okay. Do it. I might make it. All right, consider the following data. Let's see, we've got calcium graphite, use calcium carbide, 5 equations there with enthalpies for each one. Use Hess's law to find the change in enthalpy at 25 degrees for the following equation. Okay, so we're headed for, our target is 59. Our target is this one. Calcium carbide. Every miner's friend, right, until they started blowing up. Heard of carbide lamps. Calcium hydroxide. This is the reaction that happened in every coal miner's headlamp. Until they decided to go electric. And then water? No, acetylene. Yes, there we go. That's what burns. Okay, so we want the enthalpy for this reaction, and we've got to combine reactions to get there. So let's start in order and see if we can do it that way. The first one has calcium carbide on the right-hand side, needs to be on the left-hand side, and there's only one of them. So we just need to flip the equation. We put the calcium carbide on this side. So this is our first equation, and it goes calcium solid plus carbon graphite. And the value is going to be sign reversed, plus 62.8. Okay. Now, that takes care of this one right there. All right. How about, what's the next one? Calcium oxide. Let's work our way down. Calcium hydroxide. Calcium hydroxide and water, the third one down. Puts water on this side, calcium hydroxide on that side. Right, okay, so let's do that. Calcium hydroxide on this side. Correct? Aqueous calcium oxide plus water on this side. See if I got it right. Yes, yes, yes. We put them in the same order. We didn't change anything. So our value here is minus 653.1. 0.1. Okay, that takes care of this one there. And one of these. Okay. How about acetylene? Acetylene is on the wrong side. We need to put acetylene on the right-hand side, and there's only one of them in the equation. So we just flip it and put the acetylene plus 5/2 oxygens on the right-hand side. So 5/2 oxygen plus C2H2 gas on this side. And then on the other side is 2 carbon dioxide and 1 water. There we go. So since we flipped it, it's plus 1300. And that takes care of this one. That takes care of these 2 waters. Right? So that gets everything. And let's see. Which one have we not used? We haven't used the last one or the second. So we don't have any carbon dioxide up there, but we do have carbon dioxide here. So we need one with carbon dioxide on the right-hand side. Right? Yeah. And that's the last one. Carbon dioxide is on the right-hand side. That's good. But there's only one of them. So we actually need 2. We need 2 graphite. 2 graphites. I'm multiplying this in as I go. 2 oxygens yields 2 carbon dioxide. And all we did was multiply by a factor, which means minus 393.51 times 2. Point. Okay. So, there must be, what did I do wrong? Well, why did I do 2 here? I didn't need 2, did I? No, I just need 1. That's simple to fix that. I was going off of carbon dioxide, I think. So we just need 1. All right, so that takes care of this one. Right here. Carbon dioxide. That's why I did it, because there are 2 here. Which one we haven't used yet? Second one. Well, I don't have any carbon dioxide in it. So I've got carbon dioxide that I don't need. Did I write that one correctly? CO2 plus water. 2 CO2 plus water is 1. This equals 1 of these. And 5 halves of that one. You see what I've done down there. CO2. Okay. Calcium carbide, that one's right. No, that one's not right. I wrote this one incorrectly. Calcium carbide, 2 graphites. This needs to be 2. 2 and 2. And this does need to be 2. See where I made my mistake? I wrote this one incorrectly. Yep. So it takes care of that one. And 2 CO2s. Right? Oxygens. Oh, we got another one that we need to use. Calcium, a half oxygen, and calcium oxide. Right? Because I got to get rid of this calcium. So on that side, so the second equation puts calcium on this side. That's good. Calcium plus 2 graphites. 2 graphites. Yeah. Yields calcium oxide. And that's minus 635.5. Okay. So,
Where'd you get the 2?
wait a minute.
It should be a half oxygen.
Sorry. I was looking at the wrong one. There we go. It would have dawned on me eventually. So 2 oxygens is 4 halves. 4 halves and 1 half is 5 halves, and there's 5 halves. So these oxygens are gone. And this calcium is gone. And let's see, calcium oxide, that one's gone also right here, and there. Okay, let's see. Are there any not crossed out that need to be? That one's good. That one's good, along with this one. Calcium hydroxide's good. Acetylene's good. And the rest of them need to be crossed out. Okay. Now we can add things together. Let's see, I'm gonna go ahead and multiply this one. 393.51, change the sign and times 2. And then 635.5 minus 1300 plus 653.1 minus and 60.8 plus. So I got, let's see. Okay, that one doesn't have any decimals after it. So I have to stop at 713. Negative 713. There it is. Needed to be rounded off, actually. Okay. All right, that was 59. Let's see. Oh, okay. This one looks familiar. So I have molecule A, B, and C. What are we doing? Got 15 minutes. Let's see, we have 1, 2, 3, 4 across and 4 up and down. 6. Yeah. So this is electronic structure and hybridization. And angles. Okay, molecule A, B, and C. I'm gonna put a D out here in case I think of one. We start off, we're given hybridization on A is sp3. So now, let's give it a color. I think purple works good. Yeah. So for A has that hybridization, central atom, molecule B has two more effective pairs. If it has two more effective pairs, that means these are all used up, one S and three Ps. So this would have to be D2 sp3, two more effective pairs. And C is diatomic, consists of one sigma bond and two pi bonds. If it's diatomic, one sigma and two pi's, right? Sigmas, pi's, pi's. It has to be a triple bond. And that means the hybridization on each one of these would have to be sp, because you'd need unused p orbitals to overlap for one of the pi bonds and another set of unused ones to overlap for the other pi bond. Okay, and then the hybrid orbitals would be would give you the sigma. So this one would have to be sp hybridized. Okay, that means electronic structure. Okay, we can say linear, and this would be octahedral. Right, 3, 4, 5, 6, and this would be tetrahedral. Okay, what are the bond angles? If you do have all of the positions occupied by atoms, then your bond angles here would have to be 109.5 degrees. That's your starting point. Octahedral, sometimes I have to draw. And then we'd have something up there and something down there. And we'd have this bond would be right angle, right? All these bonds would be right angle here. You could have possibly this bond at 180. So for octahedral, the possibilities are 90 and 180. Linear, of course, the only thing you can have is 180. Okay. Now let's see. If D had one more effective pair rather than two around the central atom, then its hybridization would be just D sp3. Right, so that'd be 5, which means trigonal bipyramid. Okay, and what would its possible angles be? Well, let's see. If every position is occupied around you have something in the middle. Around the central atom is 120 degrees, right? 120, 120, 120 makes 360. So 120 is a possibility. And then if you go from here to here, go down and then right angle, that's 90 degrees. And then if you have something here and here, oops, that's 180. So the maximum number of bond angles you could have for this one would be 129 and 180 possibilities.
And that's if it has one more pair instead of two.
Uh-huh.
Okay.
Yep. Yeah, if we start from here and say just one more effective pair, that would lead us to this one. Is that the last one?
Mhm.
Oh, okay. All right. Well. since we did every one of them, I don't have any place to go from here.
Could we do another one like 59? Cause I get confused on that.
Oh, yes.
That one really gets, that one really gets me.
Okay.
I'll see y'all to these things.
Okay. Let's see. I don't have one right off the top of my head. Maybe if I go, let me go back to the chapter where we did these heats. Let's see, we'll do that one. Do that one. That's some structure. This one is what? Thermochemistry. Is that it? What about this one? That's gases. That's so it has to be thermal. Let me just take a quick look here. Yeah. Excuse me. So let me look at the review document for that one. Should be able to find that. That's the kind of thing I can't pull out of thin air.
Yeah, I get confused on how you know how to flip it and all that.
Oh, okay. Oh, we got several to choose from here. Let's see. Thanks. All right. Okay, let's see, let's pick one that's doable. These are showing me standard enthalpy of formation using S. Do that. What's TE? It's not thorium. It's like, maybe it is thorium. No, here's thorium. Thulium? I can't remember what that one is. We have three component equations that we could use for this one. Let me take a second to see. I could make a really simple one. Let's try that first and see if it rings a bell. This in the review document for chapter 6. This is number 65. This is chapter 6, number 65, for reference purposes. Okay, this one says use these two equations, and I should write them up here. That one and this one yields 2CuO. And the delta H for this one is minus 144 kilojoules. Okay. And the other one we have to choose from is Cu2O yields Cus plus CuOS. And this delta H is plus 11 kilojoules. Okay. So we're not given, in this problem, we're not given the target equation. It just says use these two to calculate the standard enthalpy of formation for copper 2 oxide. So you have to be able to write that equation. So we start with copper 2 oxide. We work backwards. A standard formation would be this copper in its most stable state at room temperature and pressure, and the same thing for oxygen, which would be diatomic gas. So we need half of that one. That's our target equation. Right. Now, first thing you'll notice is that copper 1 oxide is not in this equation, but oxygen and copper 2 oxide is. So I would use, let's see, rather than having to make so many changes, I would use this one to give us this right here, because it's only one and it's on that side. Okay. All right, so let's use the second equation. Yields copper plus, hold on a second. No, that's not gonna do it right. Let me check it, be sure I put everything up here right. Now, calculate the standard enthalpy formation for this one. Okay, that's correct. Yeah, that's correct. You know what? That's the wrong approach. I'm gonna start from the left-hand side. If I put copper on this side, I know I'm gonna need copper. So if I put copper on this side, that means I have to change the sign on that value. So if I flip this over and put copper plus copper oxide, copper 2 oxide yields copper 1 oxide. And that gives me 1 copper here, 1 copper there. Okay. And that means this has to be minus 11 kilojoules. So we've used this one. Now I need copper oxide on this side, and it's already there. So what would happen if I just brought that equation down to here? Let's see what it would look like. Right, we know it's in the right direction because the arrow says that's on that side. We need this on this side. Right? So they're on the right side.
Okay.
And that means we can keep this exactly as it is. Okay. Now, what does that give us? This is our target. Then this copper 1 oxide and that copper 1 oxide will cancel. Let's see, we need copper 1 oxide there. Did I write that correctly? Okay. I got too many. Right, I got too many of these. Oh. That's gonna cancel one of them. And this one cancels that one. And that leaves me with copper. And then half oxygen. And one copper. That's it. Now let's add these together. Minus 155 kilojoules. I don't know, did I confuse you even more? Because sometimes it just happens.
Yeah,
What you try to do is be as methodical as possible about it. And whenever you have to, you always go back to your target equation. Whenever you have to have one of these compounds or elements on one side using these contributors, then you match the number of them. And if you have to multiply by a whole number or even a fraction, you have to multiply that times the delta H.
okay,
If you have to flip it to get the compound or the element on the correct side. Now, the correct side relative to the target equation is it wants to be on that side where it's at. But if you already have that one there and you introduce the factor that's not in the target equation, then you want to flip it so that you get it on the opposite side and cancel.
okay. That makes more sense.
Yeah, that's okay. I should have said that at the beginning.
Well, thank you for doing another one and helping me out on that.